you first. So good afternoon, everyone. I'm here of introducing Jan Horak as our speaker for the seminar today. Jan graduated from Heidelberg University in 2017 with a Bachelor of Science in Physics. His undergraduate research focused on modern X collider searches for dark matter. He also spent 1 year in San Diego State University in 2015 and 2016. After graduation, he then continued at Heidelberg University, where he received his Master of Science degree in Physics in 2019. His master thesis focused on spectral functions from Dyson-Schwinger equations with dimensional regularization. Now, Jan is currently a PhD student at Heidelberg University, working with Professor Jan Pawlowski. His most recent research work and the topic of his talk today is the real-time physics from Dyson-Schwinger equations via spectral renormalization. Please join me in welcoming Jan Horak. So Jan, please.
Yeah, thank you very much for the kind introduction. And thanks to the authors for the invitation. I'm honored. Yeah, I have the pleasure to talk to you today about work that originated mainly from my master thesis, but also the last few months, starting my PhD. We recently published some results, which you can find on the archive link on the title slide, about scalar theory. And yeah, as said, I'm going to talk about real-time physics from Dyson-Schwinger equations via the spectral renormalization. To start, I'm going to give you a brief outline of what this talk is going to contain today. I have two main parts. The first part is to introduce a little bit the tools we used and we developed. I call it spectral approach to real-time. I'm going to motivate what I'm going to talk about and introduce to you the novel scheme of spectral renormalization we developed during the past months. And then I'm going to apply the scheme to two different models. First of all, I'm going to into the scalar phi-4 theory in 3 dimensions. And then I'm going to go briefly about some preliminary results on Young-Mills theory. Yeah, you'll see later. So then, yeah, I'll just get started and talk to you a little bit about the motivation for what we're doing. So we want to do real-time quantum field theory. Why do we want to do this? First of all, it's very important if you want to resolve any kind of time evolution and dynamical processes and time-like physics in general, that you have access to real-time quantities. And there's few popular common examples for this. So for example, generally non-equilibrium phenomena, transport coefficients in heavy ion collisions, hydrodynamics needed, transport in general, any kind of bound state physics really benefits from real-time quantities. So this is what we want to do. And as I said, we want to do this in a quantum field theory framework. And as we mainly deal with strongly correlated systems, especially in the low energy regime, this usually asks for non-perturbative techniques within this quantum field theory approach. And there's a few popular ones, which I'll briefly mention here. So there's lattice theory, which, yeah, I guess you all are familiar with, very well tested tool. Then there's functional methods like the FRG, which is worked on a lot in my group in Heidelberg, especially from my supervisor, but also other groups in Heidelberg do that a lot. And then also, of course, 2PI approaches, which is, for example, in Heidelberg also done a lot by the group of Jürgen Berges, which also extracts real-time results and recently for scalar theories as well. What do all these approaches have in common? They build on a Euclidean formulation of quantum field theory, which means they don't take place in Minkowski spacetime. and this has calculation reasons. It's just easy to calculate there. If we want to resolve any kind of real-time physics, we need to somehow get back from the Euclidean space to Minkowski space, and this imposes a severe challenge because within the approaches you deal with, often numerical methods are involved, like multidimensional integrations or partial differential equation solvers, which are usually treated in a numerical way, and this usually hinders access to the complex momentum structure. And in this way, one has to come up with some more sophisticated methods to really perform this non-trivial map back from the Euclidean space to the Minkowski space. And more or less two approaches which are known to me. First of all is an numerical reconstructive approach, which basically relies on a inverse transformation of the integral transformation, which connects the correlation functions in Minkowski and Euclidean space. And this is done a lot. This is shown to work a lot, but this is in general such an inverse integral transformation numerically is an air-conditioned problem. And this is why often these results are plagued by large uncertainties. And we want to try and take a somewhat different approach, which relies on direct real-time computation. And how to do this, as I said, I mean, this is not given necessarily, because you really need to have full access to your momentum structure. And this is what I'm gonna roll out to you in the rest of this talk, how we want to do this and how we want to proceed with this. This is about real-time quantum field theory. Next, I'm going to talk a little bit about our non-perturbative tool of choice here, which are Dyson-Schwinger equations. I'm not going to go into too much detail here. In general, Dyson-Schwinger equations can be considered as quantum equations of motions of the theory's Green's functions. So if a differential equation, if you solve this, you have the respective Green's functions. You see example of the scalar theory here. This is the Dyson-Schwinger equation for the propagator. What you can see in this example, there's not only the full two-point function, which is denoted by a gray blob in general. I mean, the notation is explained on the right. Large gray blobs are really full quantum vertices, and the black dots are the classical vertices. The internal lines are full propagators, so this is really a non-perturbative equation. And what you can see here already is that the equation for the propagator also involves full 3 vertices and also one full 4 vertex here in the sunset diagram. And this hints already at the fact that generally you get an infinite tower of coupled differential equations here, differential integral equations here. Which is per se, I mean, it's an infinite tower, not solvable. So you need to, at some point, have some motivation to do some approximation. So you want to truncate this infinite tower of equation at some point. And this is usually done within various kinds of approximation to these vertices. On a more general note, you see below the master Dyson-Schwinger equation, so with the quantum effective action as the central object in non-perturbative functional approaches, which arises as the Legendre transform of the Schwinger functional and is the generating functional for one particle irreducible correlation functions. And you can, in principle, generate any endpoint function by acting with the respective functional derivative onto this equation. Okay, so far so good. Excuse me. I'm gonna continue. I think Dyson-Schwinger equations are fine for now, and I'm gonna come to the next tool we need in our spectral approach to the Dyson-Schwinger equation, which is the Källen-Lehmann spectral representation. I think most of you are familiar with this representation. It is a representation for the full Euclidean propagator G here, and it is an integral representation. You can see the spectral function rho, and then you see the spectral integral and the perturbative propagator kernel p squared plus lambda squared, and you integrate, if you wish, overall spectral mass lambda. And it is a very handy representation. You can see already by now, because if you look at the momentum structure of this object, you see basically just a classical propagator here with a mass lambda. And this already suggests that this can be very useful in the calculation. The spectral function rho below, you can see here, is related to the propagator by the inverse transformation, and we get it directly by the imaginary part of the retarded propagator. And as you can see already now here, this is a fundamental real-time object, because as we can see on the right-hand side from the plot of the complex plane, discontinuities along the positive real axis is really what make up the spectral function. So you can get a very intuitive complex analysis approach to the spectral function by Cauchy's integral formula, and there you can see very nicely how the spectral function arises as the set of all discontinuity or non-analyticities of the propagator in the complex plane. And in consequence, as this is related to the full propagator by an inverse transformation, rho really carries all non-perturbative information which is contained in this full two-point function. And what's also suggested by the little figure on the right-hand side is that the existence of the spectral function really imposes tight restrictions on the functional space the propagators can live in, because there's also a few symmetry properties which go into the existence of such a representation, and this is really important to note here, that the existence of a spectral representation has tight or strong implications for the analytic structure of the propagator. Yes, and then there's another point I want to mention. I mean, I think it's a kind of natural question. So we have a two-point function here, and it has a spectral representation. How about higher correlation functions? I mean, if we find such a very handy representation for the propagator, might it not be possible to find spectral representations also for 3 and 4 and higher correlation functions? And I'm going to come back to this later, because the spectral representations, at least in the scalar theory, are also motivated from an axiomatic standpoint by quantum field theory axioms. Okay, so yeah, having introduced these basic tools we're going to use, I'm going to come to the little bit of working example, which is the spectral DSE for the scalar phi to the 4 theory, already flashed before. So what we're going to do is we're going to consider the propagator Dyson-Schwinger equation for the scalar phi to the 4 theory in the broken phase, which means we have a non-vanishing field expectation value, and you can see the full Dyson-Schwinger equation here, not truncated. So this is the DSE in its initial form with the full vertices, all full propagators on internal lines, and few classical vertices. And we can recast this diagrammatic equation in an algebraic form on the left-hand side. This is the general form of this equation in 3 dimensions, where we just have the classical propagator, inverse propagator as p squared plus m phi squared, where m phi is the renormalized mass here, and then a sum over loop diagrams we denote as dj here. And of course, I mean, if we want to treat this equation in some way, we need to come up with representations for the full vertices. That is why we're going to start with some assumptions. So this leads to our setup. So we plug in this representation for the full propagator on all internal lines. And then we, in this first working example, we need to assume a certain form of vertices which allow for the below form of diagrams. So what is this form? It is vertices which either have a canonical momentum scaling. What do I mean by this? I mean by this that they just scale with integer powers of external or a loop momentum, or they have a spectral representation, which would be the best case, because then we were really able to treat the full vertices in their full glory. And if we take this assumption, we can recast the general DSE in the top left corner in the below form. So the diagrams dj can be reformulated as a product over spectral integrals. One spectral integral comes with each internal line from the spectral representation of each propagator. And then we have some momentum integral ij, which is given on the right-hand side below here. So what is this momentum integral ij? It is certainly a product of all the different loops in our diagram. And then we have loop integration qk, and then also a product over all classical propagator kernels, lambda I plus li square, where li are just linear combinations here of the loop momenta and the external momenta. So yeah, it's really important here I want to emphasize, so that these are all, I mean, basically that it's classical propagators on the right-hand side. So you have loops, and then you have these spectral representations, and they give you classical propagators with I different masses, lambda I, but this really makes this momentum integration over the loop momenta to perturbative momentum integrals. So this is something we can deal with. I mean, the perturbative community has, thank God, quite well working hard to compute these diagrams with different masses for many diagrams on many different topologies on all lines. And that's why, in general, the integrals marked in the blue box are something which is known from perturbation theory. So just a product of nj different propagators with different masses. And then we still have a second integral, which is the spectral integral, which we want to solve which we need to solve if we want to have a result for our loop integral about our loop diagram dj. And this is highlighted on the left-hand side in red. And this is generally a non-perturbative integral, because the spectral function, as I said before, carries all the non-perturbative information, and also generally is not known algebraically and analytically, and often just has a numerical representation. And yes, so this is where we are. So we inserted spectral representations for all the propagators. We made a quite loose assumption on the representation of the vertices in our propagator DSE in the scalar theory. And what we end up is, just by these two ingredients, is with perturbative momentum integrals, which are usually known from perturbation theory, and some non-perturbative spectral integral, which also needs to be performed. And the next task is, I mean, we want to evaluate these integrals, which is luckily doable for the momentum part, but not so trivial for the spectral part. And also, of course, we have to deal with renormalization. And this is what I'm gonna explain to you next. So I'm gonna come to the spectral renormalization in general. I mean, the loop momentum integrals I denoted as ij before, as I said, are perturbative, so we can really fundamentally treat them in dimensional regularization. So we have access to all the momentum structure. We can plainly apply, I call it naive textbook DIMREG on the momentum part, and then we have a solution for the momentum integrals. We can just plug in for all our loop integrals, and what we're left with is the non-perturbative spectral integrals. And here, to be consistent in our dimensional regularization scheme, we would really need an analytic expression for the spectral function in order to perform dimensional regularization correctly, which is taking the limit of our parameter epsilon, which we introduce usually in general dimensions D, after all the integrations are performed. Because what we're doing here is we're swapping wildly orders of integration and limits, and I mean, this is fine as long as everything is finite. So if we take this limit before really evaluating all integrals, we might run into some severe problems. And this is something we can only do if the spectral function really is given in terms of an algebraic closed form, which enables us to really single out the dimensional divergence from the spectral integral, which these also carry, which gets quite clear if you just consider the previous equation in dimensional analysis. So in general, this is not the case for rho, so we have some numerical input for a spectral function, and then we need to come up with some tool in order to regularize the spectral integral. And this is what we call spectral renormalization, and what we try to brand a little bit here. So it really is, I call it a novel renormalization scheme, because to our knowledge, it combines these ingredients of spectral representations and dimensional regularization in a form we've not seen before. And this splits up in two different sub-schemes. So the first sub-scheme is called spectral dimensional renormalization, which we take as the scheme which treats the case where we can analytically separate a known UV behavior of the spectral function. So we have some spectral function rho. It might only be in a numerical form, but from the perturbative tail of the propagator, for example, we can infer the UV behavior via the inverse transformation between rho and G. And by inferring this UV perturbative tail of rho by the propagator, we can subtract the analytically known UV part of rho from the given numerical input, and basically by this lower the degree of divergence in the ultraviolet of the spectral integral, because rho is effectively dropping off faster now, and of course we need to add this UV part we subtracted of the numerical input as well, and this basically leaves us then with a integration we can really perform analytically, because we know the analytic UV behavior of rho inferred, for example, from the propagator. And this leaves us in a situation where we can treat the UV part also in dimensional regularization, because this is a fully analytic expression. And by this, we really normalize our equation in a full dimensional regularization type scheme. And this has the consequence that we really preserve all symmetries of the theory. So for the example of our scalar theory we presented here, these are Z2 symmetries, for example, but also if applied to gauge theories, this especially preserves gauge symmetries, which is a very nice and handy feature. But one has to say at this point that the analytic evaluation of the spectral integral is usually much more sophisticated and complicated than just the perturbative momentum integrals, and really impose some analytic challenge. Okay, there's a second sub-scheme to the spectral renormalization, which is the spectral BPHZ renormalization. This is something we need to come up with if we take the limit in our dimensional regularization scheme epsilon to 0 before performing the spectral integration. As I explained to you before, this is actually, I mean, I would say not allowed because the spectral integral carries divergences. But then we need to come up with a way to subtract these divergences again from the spectral integrals, and this is something we do in a BPHF type manner. We just expand the integrand under the spectral integral in orders of external momentum, for example, and subtract order by order the leading and subleading divergences. And this is well suitable for numerical applications because it is especially easy to implement, and also a really robust scheme. And one has to say though that both schemes really consistently normalize. In this case, the Dyson-Schwinger equation to all orders here, and is consistent because it really only bothers with the renormalization of the explicit topologies given in the equation, and it is built on the use of finite full vertices as well. All right. So having set the stage, I'm going to come to the explicit calculation we're doing here. So I introduced the renormalization scheme we used. I introduced Dyson-Schwinger equations and also the spectral representations, and then we're going to throw all of this onto the phi to the 4 theory. And what we're going to do is we're going to treat the phi to the 4 theory in the skeleton expansion, which means you dress all vertices. You might have noticed here there's a diagram missing, which is the squint topology. I'm going to come back and show you 1 second. On the very right hand side, the reason for this diagram missing here is that when dressing all vertices here, the prefactor of the squint by matching to perturbation theory effectively becomes 0, and is, if you wish, absorbed as a vertex correction in the second full vertex of the polarization diagram here. And this is the equation we're considering. So we have full vertices. We have all our diagrams. We know how to renormalize them. And this is so far still Euclidean equation. And by the input I presented before, we really have all the analytic structure of the in momentum space here, and we can just you can call it analytic continuation, but basically it's just evaluation of this above diagrammatic equation on the real momentum axis by replacing the momentum by what is given here. So I really just evaluate my function fundamentally on the real momentum axis and carefully take the limit epsilon to 0. I say carefully because usually you get 0 crossings at some point, and in functions arguments, and this can lead to distributional contributions to this equation. You need to be careful to consider also, and to not lose them by just blindly taking the limit. But yeah, so we evaluate our equation in real time, and then we're basically good to go. So we can start computing. What do we need to start computing? We need an initial guess to plug into this equation. What we want to do is we want to solve the Dyson-Schwinger equation by iteration. So we start some initial guess for a spectral function, plug this into the equation up here, see what comes out on the right-hand side. If I plug in my initial guess rho 0 everywhere, I can calculate, I have calculated then my real-time inverse propagator here, and from that I can directly infer via the inverse relation between propagator and spectral function. I can directly infer the spectral function, again, plug that back into my 2-point function, and iterate the system as so long till the solution converges. I'm not going to really go into the details of our convergence condition here. You can say by eyesight if you wish. No, but we also applied some little bit more quantitative here. Yeah, what I want to mention here is that if you look back at the general form of this equation down here. So this is gamma 2. Of course, we have still Euclidean momenta here, but it doesn't matter. What's really remarkable about this calculation is that the only thing that gets updated through the iterations is the spectral function rho. So all the momentum part here stays the same once evaluated. So we evaluate these integrals, and we only plug back updated spectral functions row into this equation. And this makes the whole thing a very robust scheme, because it's computationally cheap, if you wish. You only need to evaluate these multidimensional spectral integrals in each iteration, and that's all there is. So it's really all the non-perturbative information in here, and you only need to evaluate integrals at each step of the iteration. So far, so good. There is another approximation we're going to apply to the above equation. As I said, we have to deal with for vertices here, and we need to at some point specify these. But first, we're going to eliminate one of these vertices, which is by the self-consistent Källen expansion. And what is this? So consider the 3-point function, gamma 3 here, and we consider the 3-point function in a vertex expansion, which is given above. So we expanded about some non-vanishing field expectation value phi c, which is evaluated at the equation of motion given by the minimum of the effective potential in a derivative expansion. And coming back to a somewhat different form of the equation, so we replaced the initial polarization diagram with two full vertices again by its initial form, and added again the squint topology here. And what we note here is, when we look at this equation, is that by the above vertex expansion of the 3-point function, we can find a general identity, which I will explain to you. I know it's a little bit cryptic and very bad notation, and also probably abuse of notation. That's why I'm going to take a little time to explain to you what's down here. But what it does is it allows us to express all diagrams in the above equation which have 3 vertices, either classical or full, to re-express all these diagrams solely by the full 4-point function. And how does this come about? So just consider the above equation. So each of the 3 vertices here carries, by the vertex expansion of gamma 3, at least one external constant field here. And if I now act on this equation, you see above with 2 derivatives with respect to the constant field phi c, what you see is, as these fields are not momentum dependent, you end up on the left-hand side with a 4-point function, which only depends on one momentum p, which is the incoming and outgoing momentum. And this is an S-channel 4-point function. And also we only hit the diagrams with 3 vertices by this derivative, and then we end up with this identity, which is on the left-hand side, has all the diagrams of the propagator Dyson-Schwinger equation you see above. And these are all diagrams in a diagrammatic expansion of order phi c squared, which are only those marked in blue here. So these are all the terms which are meant on the left-hand side. And but this identity basically tells us, by acting with 2 derivatives and multiplying again by 1/2 phi c squared, we can re-express all these diagrams by the full 4-point function in the S channel, subtracted by its classical contribution, which basically is this here in the DSE for the 4 vertex. And then there's an order of phi c to the Fourier term, which comes from up here, from the vertex expansion of the 3-point function. But what it says is that at order phi c squared, this is really an exact relation. So we really can fundamentally express all diagrams which carry 3 vertices by the full 4 vertex subtracted by its classical contribution. And this is something really nice, because it allows us to fundamentally eliminate the 3 vertices from this equation, and this replace them by the 4 vertex multiplied by the field expectation value squared, and leaves us with an equation for gamma 2, which only depends on the full 4 vertex here. And this is something very nice. So the only thing we are left with now in order to start computing is to specify what our 4-point function in this scheme is. And this is what I'm going to come to next. So, excuse me. what do we use as a 4-point function here? So we use a resummation of an S-channel expansion, which you can see here. So it's basically a bubble expansion in the S-channel, and this you can geometrically resum and with the closed form on the right-hand side for gamma 4. This is what we use. You might say, no, okay, well, before you argued away this squint topology by absorbing it into the 4 vertex, and now you don't resum it anymore. This is correct. This topology is effectively neglected by using this form of 4-point function, which is not a conceptual problem. It's just for simplicity, we might as well include it. But yeah, that was at that point beyond the scope of my work. So, I mean, you might know this expansion from large N schemes, and there it is known to be a good approximation by the closed color loops inside. But as we already consider n equals 1 here, this is not necessarily well justified, and nevertheless, we're going to stick to this here and use the 4-point function as shown on the right. But you might say, no, okay, well, I mean, you told me before that you need a certain form of vertices with a canonical momentum scaling in order for your whole perturbative momentum integrals stuff to work. And this form of gamma 4 on the right-hand side does not really look like it has a form of canonical momentum scaling. And this is correct. And that is why we needed to come up with a representation we can use for this 4-point function in our calculation. And this is indeed a spectral representation. So this is more like a sophisticated guess. I mean, it is known that also higher correlation functions have these spectral representations in different channels. And as this is the S channel, we just gave it a shot and tried to find such a spectral representation, and we could really empirically confirm this. So this is the general form. It basically looks like the propagator spectral representation. It has a spectral kernel here, a spectral function here, gamma rho 4, and then the spectral kernel. Note that the difference is that we have some finite real part here, constant real part here that we need to add to gamma 4. And as before, the rho 4 is obtained by the imaginary part of this very correlation function. And yes,
can I ask you a couple of questions? So
yes,
gamma
sure.
4 is the full, basically amputated 4-point function, right?
Yes.
So it doesn't only have the S channel bubbles; it also has the T and U channel bubbles. So that means it must have a left-hand cut, which it's unclear if in this integral form you are taking this. I mean, if I assume this is basically the same integral that you were writing before, it looks like it has only the right-hand cut.
Yes, it only has the right-hand cut because I mean the T and U channels are not present in this bubble expansion.
Okay,
if I understood you correctly, so this is really an approximation to the full 4-point function. It's just one channel, right?
That's fine. So that's the strongest approximation because, of course, they should.
Yes, it is. It's a very strong approximation, and you're completely right.
Yes.
Maybe I was not clear enough on this. But further, it is an approximation we need in order to for this previous scheme to work. So as I showed you here, the replacement of these two diagrams really necessitates an S-channel 4-point function. Right? So this fits. Yes, so this is the S-channel, and it has a spectral representation, and we were able to basically empirically show that this is
I mean, just since I already interrupted you, just to clarify the notation. So all these functions are still in the Euclidean, right? P is the Euclidean momentum.
Yes, yes.
Okay, so then you mean to analytically continue at the end, basically. So now you are defining your schemes. Okay.
Yes. So I mean, for the I forgot to mention this. So as for the 2-point function, I mean, we can directly evaluate on the real momentum axis, and this is the same thing we can do for the 4-point function. We can this diagram here, which is the only momentum structure which goes into. So I marked it in the red box. It's pi of p, which is basically the fish diagram or self energy with some coupling. And the phi squared, it's from its analytic structure here identical to the polarization diagram in the propagator DSE. And
yes,
we know that
that's only
diagram, and
that's only because of the approximation you're using. In general, it's not.
Yes, of course, you're right. That's due to the approximation. But this has the consequence that we, as for gamma 2, we can directly evaluate on the real momentum axis, also
Yes.
this correlation function.
Just last question, then I don't back you again.
Sure,
why
of course.
Why you are in 2 dimensions? Because now your phi to the 4th is super renormalizable. Is
yes,
that a
you're right.
for that, or just?
Okay. So this was a point I was to mention that. So in 3 dimensions, there is a bound state in this theory. This was seen in early lattice calculations by Hasenbusch et al., for example, in Heidelberg, but also by Bertrand Delamotte in an FRG framework with BMW type vertex approximations, and this was something we aimed at first. Yes.
Okay.
But haven't seen it yet. But I'm gonna come back to that point later.
Thank you.
So yeah, of course, you're welcome. So this is the, I mean, if you wish, empirical confirmation that the spectral representation exists and works. So on the left-hand side, you really see the Euclidean correlation function. The solid lines are for different coupling configurations, just the Euclidean correlation function in its initial form, as was shown in the red box highlighted before. And then you can see the dots, which are the discrete momentum points evaluated via the spectral representation, and they perfectly fit. So this is really a good fit, and the spectral representation seems to hold for the 4 vertex in the S channel here. And on the right-hand side, this is these are the spectral functions. They are negative. Why are they negative? It's just, I mean, it's basically convention. So the one loop correction, the classical contribution to the 4-point function has a negative sign, and as you can see, the curves here on the left-hand side all approach their classical value in the UV. So the green curve goes to 20 as the classical coupling is, and the corrections are negative, and that's why the spectral functions are negative. But besides that, there's not much to it. So structurally, there's a scattering tail here, which encodes all the scattering and the higher order scattering processes of which pop up in this correlation function. But with these ingredients, so we have spectral representation. Yeah, on a more technical note, we get these results by iterations of the DSE, and it really converges quite quickly. So that means less than 10 iterations, and iterations take really few minutes. So it's computationally really cheap and powerful. And yes, so this is the propagator spectral function. We really computed directly, real time, without any use of reconstruction techniques. We can also look at the respective spectral function for the 4-point function. We can deduce from our results. This is shown here as before, negative. As I mentioned, you can again see the onset, the scattering onsets here of the 2-to-2 scattering process here at twice the pole mass. You can see also here the three particle onset at 3 times the pole mass. So it's basically the correction of the quantum correction coming through the 2-to-3 scattering process, which shows up in the scattering tail of the vertex spectral function. And of course, this spectral function does not have any pole, because that would be a resonance in the S channel, and that would be some additional resonance in our theory. But we haven't seen anything like that here. All right. So this basically concludes the phi to the 4 scalar theory part, and I'm gonna use the last few minutes to briefly go over the Young-Mills part of our calculation. So we basically took the whole methodology we developed and I explained to you before, and tried to solve the gluon DSE, which is shown above at one loop here. I need to emphasize here, this is a proof of concept. So we did not yet, I mean, this emerged in my master thesis, we did not really match to any numerical results yet. It was more like the question, are we able to, in general, solve this above equation in a spectral representation for gluon and ghost at some point in parameter space? And as we only consider the gluon DSE not coupled to any equation for the ghost, we need to come up with an ansatz for the ghost spectral function. We use what's shown on the right-hand side below. How is this motivated? So we basically looked at a proximate scaling behavior in the infrared for the ghost, and from this known momentum scaling of the propagator, we try to induce a spectral function, and this was shown to hold. So the ghost propagator has this representation, and we just use it here because we really want to fix the infrared behavior of the 2-point function of the gluon to be negative. So the backbending, the derivative of the gluon propagator in momentum in the very infrared, we want to have positive, and then that's why we include the ghost contribution here to really fix the known infrared behavior in the scaling scenario of the gluon DSE. Yes. And again, we renormalize here via our spectral BPHC scheme. We plug in classical vertices everywhere, also where the full blobs here are. And then we again try to solve the Dyson-Schwinger equation with the dynamical spectral function for the gluon. And this was shown to converge and yields a result which looks like this. So what are the qualitative features here? We see a slightly negative behavior in the infrared, which we, if you wish, put in by hand by assuming the form of the ghost propagator or spectral function I showed on the previous slide. So the ghost loop really accounts for the negative infrared behavior, and then at some point the gluon dominates, and we have zero crossing here. And we have a very large positive peak. You can see in the inset up here. So it is almost like a delta pole. It's fundamentally not a delta pole, but it is a very strongly peaked structure. And then we have the negative tail in the spectral functions, which is known also analytically from perturbation theory. So this is you might say that it has all the qualitative features which you would expect from other schemes, but we really, I mean, just tuned our equation to find some point where we really have a solution in the spectral form, and this is something we could show by this. Yes, so we compared what our result, which I need to emphasize again, is very preliminary, to other results obtained, for example, via numerical reconstruction from Euclidean data obtained in the functional renormalization group here by collaborators Jan Pawlowski and Niklas Wink, and also by Anton Schirol and Alexander Rotkopf in 2018, and they reconstructed this form of gluon spectral function from the FRG data by Bayesian inference, also assuming a certain form of functional basis for the propagator. And if we compare these two, the qualitative features are similar. Quantitatively, we're not there yet, but so far this is a very promising result, which lets us believe that we might be able to update our scheme in a way that we get closer really to physical results and still keep a spectral representation fundamentally for the gluon propagator in this Young-Mills theory. And yes, with that, I'm going to conclude my talk. So what have I talked to you about? First part was more on the toolbox side, on the technical side. So I introduced spectral renormalization, which is a novel renormalization scheme, and it builds on two things, which are DIMREC and spectral representations for spectral functions, used here for the propagator, but can be also applied for spectral representations for higher correlation functions. It splits up into subschemes, which is for once the dimensional spectral renormalization, which is fully gauge invariant when applied to gauge theories and preserves all symmetries of the theory at hand. And the second subscheme, more suitable for numerical applications and easy to implement, is the spectral BPHC renormalization, which we used in the two model examples I showed you. And this renormalization scheme really allows for a direct real-time calculation of a fully renormalized equation. And then I went through two physics examples with you, which is the scalar phi to the 4 theory in 3 dimensions, where we computed fully non-perturbative spectral functions directly from the real-time spectral DSE via a self-consistent skeleton expansion. And we talked about the Young-Mills theory in 4 dimensions, where we computed, if you wish, a proof of concept gluon spectral function. So showed that there is a point in parameter space where you can solve the gluon DSE solely using spectral representations for the gluon and the ghost. Maybe briefly on what's there to come, so future work. As I said, I mean, this is a very preliminary result, especially in Young-Mills theory. We of course want to upgrade this and really also be quantitatively competitive and match to the very precise lattice results that are around. Further, we want to include the ghost DSE to really eliminate this input parameter here and solve both equations self-consistently, fully coupled. And long-term goal is, of course, full QCD, and to see if we are able to still stick to our spectral representation for the DSE there. Generally, spectral representations for higher correlation functions are very beneficial for our calculation scheme, as I pointed out before, and this would lead to the fact that we can also upgrade our Young-Mills planned QCD calculation by inclusion of full vertices, if we're able to find these spectral representations. But this is work in progress, so nothing to report on that yet here. And coming back to the scalar theory, as was already asked, there is a reason why we treated this theory in 3 dimensions, which is the existence of a bound state, which was shown also in FRG, but also in lattice calculation. And this is something we want to be able to resolve, but it is known that this bound state is located very close to the phase transition, and this is a parameter space where we were not able to reach yet, but this is also something that is planned. And with that, I'm going to conclude, and thank you a lot for your attention, and looking forward to the questions.
Thank you, Jan, for this very nice talk for propagators, vertices, and in phi to the 4th theory and Young-Mills theory. So it's time for questions. Does anyone have any questions or comments?
You know that there are other reconstructions of the spectral functions of the gluon propagators, right?
Yes.
And they are by no means as big as these ones are. I mean, if you look at the scale on the y-axis, it's 10 to the minus 4, the spectral function.
Yes, I know, it's
right?
huge. Yeah.
So there you have a 20,000 plus the error,
yes.
So you will go skyrocketing. There are other reconstructions of the same data by Trippold at myself, in which there is no need to have this big spectral function there. Now, what I wonder is, why do you try to reproduce something that is only a guess on the basis on the basis that compose the spectral function?
Okay, I mean, I wouldn't say I'm really backwards engineering here in the way that I'm trying to reproduce some results. It's more like that.
Well, maybe then that, I mean, you really phrase that as if you were getting something that is not really there numerically, and you would work to improve that. But I don't see the need here. Actually, the peak, the negative peak there, is 4 orders of magnitude smaller, right? On your reconstruction.
Yes. Yeah, as I said, so the units and orders of magnitudes here in our results are really not to be taken for granted. So the point that I want to emphasize here is not on the explicit form of the spectral function. I mean, it is nice that we see that the analytically known infrared and UV behavior, negative behavior in the IR and UV tail also coincides with our results, and necessarily that there needs to be some positive behavior in between. We know from the superconvergence relation, but this is not the point here. The point here is that we were wondering if we are able to solve this equation in some form of spectral representation. And this is what we got out. And I looked around in my group and saw somebody that reconstructed the spectral function, and it looks kind of similar. And that's why I'm showing this here. I'm well aware of the fact that there are many other results out there which deviate largely in magnitude, and which I also need to compare to. You're very right.
I still have one question. So
yeah,
if you go back to the 5/4, so I missed what's the answers that you're using for rho for the spectral function, because you need to start with something, right?
You mean an initial guess?
So what kind of functional form do you assume, and how your result does depend on that assumption?
So the functional form we're assuming here for the 1 second, let me go back to the slide where I had it here. So you're referring to this initial guess rho 0, right?
Correct. Yeah.
Yes. So what we use for this, I mean, it's very simple. So we use, if you wish, the classical spectral function, which is for the propagator, just what gives you the classical propagator if plugged into the spectral representation. This is just a delta pole, just a delta pole located at the pole mass, which is at 1 here. Yeah. So and we do basically the same thing for the 4-point function for the initial guess there. So we know that the 4-point function has a certain form here given on the right, and it depends on the propagator and via this contribution pi. And when plugging in spectral representation for this propagator and just using the delta pole classical spectral function here, you get a certain form of gamma 4, and you can evaluate the spectral function for this gamma 4, which comes out, and this is the initial guess. So if you wish, we use the classical representations of this vertices in this formulation by as initial guess.
Okay, and then you do this iteration numerically, I presume.
Exactly. So we do this numerically.
But you want to maintain some analytic control because you want to do the analytic continuation eventually.
Yes, that's correct. So, but this works because what we do is we recompute the propagator, right? We plug in some sector function. We calculate gamma 2. This gamma 2 is, I mean, it is in terms of momentum structure evaluated on the real momentum axis, as guaranteed by the form of this momentum part here, right? And so these are the diagrams, and I can just evaluate this, and then I plug in my spectral function. I calculate the right hand side, and I get out some real-time gamma 2, and from that I just infer again a spectral function, which I can plug back into here, but I still have given analytically all the momentum structure here, because that doesn't change through the iteration. And that's why I can stably iterate on the real momentum axis. That's really a key point of the calculation here.
I mean, if I get it right, you're basically saying that the analytics, so basically the functional form of your row after the iteration is basically the same as the one you started with.
Can you repeat that again?
So the functional form of row after the iterations is the same as the one you started with. It's the same as row 0.
Yeah, not quite. So we account for two different contributions. So first, there's a distributional contribution, which is just the delta pole, which we allow for in our explicit form in the diagrams here. So basically, when plugging in some general form of row here, we allow for a pole, and we allow for a scattering tail, some continuous part of row. And the first iteration only has this pole, and we plug in this, and we get something out for gamma 2, which has a non-vanishing imaginary part, and this makes up the scattering tail then. And then also we find a zero crossing through the real momentum axis of this gamma 2, and this really gives us direct access to the pole position, which we fix by our own renormalization conditions. But that's what I meant by, so all the non-perturbative information which is generated by iteration only goes into row, which is the only thing that is updated in this equation, which makes up this calculation, if you wish. So we can we rotate to the Minkowski axis on the level of the functional equation, and then only need to re-plug in the rows we compute, the spectral functions we compute. Does that answer the question?
Yeah, okay.
There is no further questions. Let's thank Jan again. Thank you, Jan.
Thank you.